We're finishing 5.3 today. We're going to look at the fundamental theorem of calculus, which we all know basically says if you want to find the area under a curve from A to B of some function f of x, what you do is you find the antiderivative f of x and you evaluate it at B, and then you take away the antiderivative evaluated at A. And just like yesterday, we're going to continue that. What I've got here is a pretty comprehensive list of antiderivatives. And then once we've got through this list, and you can make this pretty and add to it as time goes on, but this one on the right-hand side especially is something you probably want to have handy because it's going to appear, well, the information is going to appear pretty much for the rest of the core. Okay, so let's get started. This one is the power rule. So you add 1 to the power and you divide by the new power. E to the x, I know we've got this one, but I'm putting them all in the same place now. Antiderivative e to the x. Oh, here's a new guy in town. A to the power of x. That would be things like 5 to the x, 10 to the x, anything as long as it's not e to the x. Well, you never know. I'll give it a bash. Anybody know what its antiderivative is? Or at least part of it. I'd take part of it because you should be able to guess what half of it is. Last chance. Anybody want to have a shot at it? Antiderivative of e to the x. Okay. Would it surprise you that part of the answer is a to the x? Probably not. What might not cross your mind is it's that guy. I think I'll put an example at the side. So if you had 5 to the x, its antiderivative would be that guy. Okay. 1 over x. And someone tell me 1 over x, that you should know.
Natural log?
Yeah. Now, I'm just going to call it natural log of x, but sometimes it's called the natural log of the absolute value of x. Anybody, any ideas why sometimes, even WebAssign is not that consistent, why sometimes they stick an absolute value around the thing?
Is it always positive anyway?
Yeah, it should be positive anyway, but in case it isn't, it kind of covers your butt. It's really just technical. Because, I mean, you could be finding the integral of 1 over x from -5 to -1, couldn't you? So, well, and that's probably the only case I can think of where you'd want to say, well, you can't find the natural log of -5 and you can't find the natural log of -1, but you can find the positive version. So that's about it. And we've covered these guys, so I'm going to go straight in here. This fella is negative cosine. The antiderivative of a cosine is a sine. Secant squared, just see how many people got it in their head. Antiderivative of secant squared. You should try and, excuse me, try and memorize these guys. It just makes your life easier. Secant squared, last chance.
Tangent?
Yes. I'm pushing it with that one, but I'll try it. Anybody know what the antiderivative of secant tan is?
Was it secant?
It is. And this would be very cool if you could get these, because it's such, you don't use it much. So it's one of those functions that you see now and again, and then they go away. So the antiderivative of 1 over 1 plus x squared. Think of a function whose derivative is that. That's the guy you're looking for. What function has a derivative that's 1 over 1 plus x squared, or 1 over x squared plus 1, because some people write it that way around. Last chance? I'll give you a clue and then it'll be last chance. It's an inverse trig function. Okay, here we go.
Would it be like arctangent or something like that?
It would, but I refuse to use that term. But you're correct. It's the inverse tan, which is what the thing you said is. Oh God, get out of my head. I refuse, or I try and refuse to say arc sine, arc cos, arc tan. Those are inverse tan, inverse sine, inverse cosine. I understand that, but the reason I refuse to do it is nobody else in the world except America even uses those terms anymore. It's like feet and miles. Arctan was only created because printing presses had a problem with subscripts. In this case, superscripts. It's the only reason it was there. So it's like 200 years out of date. So stop using it. Just call it what it is. Call it inverse tan, not arctan. There, I got my mump over with. I feel so much happier. Right. What is this ugly looking fella? He is also an inverse trig. Somewhere in Calc 1, you differentiated an inverse trig function, and the answer was that. That function that you differentiated is the inverse function that we want, the antiderivative function, I should say. It's an inverse what? Last chance.
Sine.
Well done. Inverse sine it is. And what looks weird, but nonetheless true, if you stick a -1 on top of it, what inverse trig function do you get this time?
Cosine.
Yeah, inverse cosine. You know, some of you are going to do engineering and your engineer professor is going to talk about an arc sine or an arc tan or whatever. And you're going to complain to him, right? You know, get into the new world, the 21st century, start doing things the way everyone else does. Okay, we have now got all those guys. So the fellas that we're going to be dealing with are going to be using some version of this, and we're also going to be evaluating it. So I've decided to put some numbers in this time. So this is question 20, or at least one like it. And it's going to be the integral from 1 to 9 of 2x plus 1 over x dx. So the antiderivative of 2x, right? It's a power rule. Add 1 to the power, divide by the new power. 1 over x gets your natural log of x, and that's the antiderivative. But we're not going to do the plus c now. We're going to do ones where you put in numbers. And so it's going to be 9 squared plus the log of 9. Take away 1 squared plus the log of 1. And that's going to be 81 plus the log of 9. Take away 1 squared, which is 1. What's the natural log of 1? What number is the natural log of 1?
Was it 1?
Or if it's not 1, what's the other most likely value? Because it isn't 1. Plus chance.
Is it 0?
It is 0. So our answer is that guy. Can we pretend for a minute that it wasn't log 9 and log 1? Suppose there was a log 9 and the other guy was, say, a log 3. That is what you would get if you had the integral, say, from 3 to 9. We need to make this look pretty, even although it's still numbers. There is a style point associated with numbers that we should get comfortable with. How can you combine two logs subtracted like this? What's it the same thing as? What's single log?
Dividing.
Okay. So if that happened, you could do that. Totally unconnected question, but you know, sometimes you might get the answer 3 square root of 20, right? That might come out as a square root question or something, right? Now that's should be tidied up as well. Can't you simplify the square root of 20? That's a way back in what, Math 99, I think, simplifying radicals. Anybody remember how you simplify the square root of 20? So, okay, what do you do?
You pull out the 2 squared from the 4.
Okay, so you call it 4 times 5, which is what you said is 2 squared. You suck it out and you get 2 root 5. So altogether you get 6 root 5. And so when you deal with numbers, the style point rules change quite a lot. Most of the time you don't have any. Most of the time the answer is just a number and that's fine. But there are some tweaks, you know, combine logs if there are any, and simplify square roots. And there are a few other ones, but I'm not sure you even see them. Nobody here would ever leave an answer as 4/8. Agreed? Nobody here would even think that that would be the right thing to do. So I guess I could have added that to the list, but it's so obvious I'm not going to. Okay, let's move on. We're going to bring 142. This is going to be the 0 to pi upon 4, at least my version is. And it's a sine theta, tan theta, d theta. Oh, my apologies. Let's write that again. It's secant theta, tan theta, d theta. Okay, antiderivative of secant tan. Antiderivative of secant tan.
Secant.
It's secant. So we're going to do the secant of theta evaluated at theta equals 0 and theta equals pi upon 4. So now you have the problem of getting exact values. No, you're not allowed to plug things into calculators and tell me the answer is 0.707 or 1.414 or various other interesting decimals like that. We need to get exact values. So essentially, we are going to have to figure out what the secant of pi upon 4 is, take away what the secant of 0 is. And that's why I said we're going to bring in some 142 stuff. So where am I going to stick it? I'm going to stick it over here. Right. Let's suppose I want to find the secant of pi upon 4. First thing I'm going to realize it's the same thing as 1 over the cosine. So that's a, I guess you'd call it an identity or a property from 142. What's a cosecant the same thing as then?
1 over sine.
Right, a cotangent.
Cosine over sine.
Which, yes, is correct. It's also 1 over tangent. Right, now, hopefully you know or remember what that guy is. And that guy is root 2 over 2. And you get that guy from your unit circle. But 1 over 2 root 2 is the same as 2 over root 2. So this guy, this little here, is 2 over the square root of 2. Take away Now let's figure out what the secant of 0 would look like. Well, it's 1 over the cosine of 0. And the cosine of 0 is 1. So it's 1. Okay, that wasn't too bad. Now, I don't know if WebAssign would accept that as an answer. Might, good chance it will. But I don't think we should leave things ugly. To me, fractions should have numbers in the bottom, shouldn't they? This is from Math 99. I think it's called, you would have heard it called rationalizing the denominator, which basically means get rid of the square root in the bottom. So in this case, to do that, I'm going to multiply the top and bottom by the square root of 2, which means it becomes 2 root 2 over 2. The 2's cancel, and isn't that a much prettier version than the original? So what we now have is the square root of 2 take away 1. And that is the end of that question. So do you see there was a little bit of style points, there was a little bit of trig, you know, a little bit of this and a little bit of that. Pretty much everything you've done from 99 onwards appears somewhere in this class, guaranteed. Okay. Let's look at a version of 23. It's going to be the integral from 1 to 2 of v to the 4 plus 4v to the 8, all divided by v to the 5. Okay, when I look at this question, pretty obvious that there's some weird fraction going on, and there isn't any weird fractions over here, so I know I'm going to have to do algebra on it. And so I have to figure a way of rewriting this so that it fits essentially this guy or this guy, whatever it ends up being. But one of these guys, right? Any ideas about how we could algebraically fix this fraction?
The denominator is a negative power.
That works fine. I like that. And then distribute it through. So that times that gets me v to the negative 1, and that times that gets me 4v cubed. I like that. And I'm really happy about this guy because I can use the power rule on him. Add 1 to the power, divide by the new powers, right? So I'm happy about that one. I'm not happy about this one right now. If you try and use the power rule on v to the negative 1, well, you add 1 to the power, which gets you 0. But dividing by 0 is bad news. So obviously that is not a power rule question. What is v to the negative 1 better written as so that we can use one of these guys over here?
Uh, 1 over v.
So when you write it like that, doesn't this now become the natural log of v? And now we've successfully completed the antiderivative part. So, you know, sometimes this happens. I mean, I didn't really know that was going to happen until later on. But just because it looks like a power rule doesn't mean it is. Would you agree that doesn't work as a power rule? Doesn't that work much better if you think of it as 1 over v? On the other hand, this works perfectly as a power rule, doesn't it? Wouldn't 4v to the negative 3 also work perfectly as a power rule? So the only power that we have a problem with is the negative 1, because it's technically going to be a log. And then you stick in the numbers. But for speed, I'm just going to do my classic ... And that just means, you know, keep going and you'd finish, right? It'd just be numbers from this point onwards. Let's look at, oh, I like this one. I wish I'd done this one earlier. For those of you who know old sci-fi series, this quote, you will know where it comes from. Danger, Will Robinson. Danger. There is something nasty happening in this one. Be extra careful. Right? So I've warned you, be extra careful. Antiderivatives. Anybody want to tell me the antiderivative of either of these two guys? Have a bash at it. Antiderivative of either of those two guys, or both if you want.
It'd probably still be 8e to the x, right? Does that one change?
No. That one is him. That's not the Danger Will Robinson one, obviously. It's this one.
That one's the one that gets ugly real fast.
It does. Why does it get ugly? What is it an example of? Doesn't look like it, but it is an example of one of these rules, isn't it? What is it the example of? By the way, that's the only one that has a name. Can you see that this is an example of the power rule? See, if that was x cubed or x squared, nobody here would have given it a second thought. But the minute you start seeing e, or pi is another one, x to the pi, you go, ah. So the rule is add 1 to the power and divide by the new power. Would you agree that gets ugly really quickly? And I just put an e there, but I've fixed it in time. It's an x, isn't it? Well, let's plug in the numbers and see what we get. We get 9 over e plus 1 times 1 to the power of e plus 1 plus 8e to the 1. Take away 9 over e plus, why am I doing this? Because you plug in 0, it's just 0. But I'll do it now, so here we go. And 8e to the 0. Would you agree that 1 to the power of e plus 1 is still 1? Right? 1 cubed, 1 to the 7. So one of these just gets you that fraction. E to the 1 is just e, so that'll get you 8e, so that's that. Nothing to the power of e plus 1 is 0, so that's just 0. And that's 1. E to the 0 is 1, so you get take away 8. And there is your answer. And there's really nothing you can do style point wise to make that pretty. So I guess sometimes you have to know when not to try and do stuff. Any questions so far? The ones we've done, are you comfortable that they all belong in here somewhere? Either right away or after a little bit of tweaking?
Professor?
Yes.
I have a question on example 20. Oh, not 20, sorry. It was 21. I was wondering if how sine theta times tangent theta became secant theta tangent theta.
Right, so the antiderivative of secant tan is secant. So in that question, you were being asked to integrate a secant tan. Okay, it was called theta, but theta is just a placeholder, it's a variable name. So secant theta, tan theta, the answer is secant. So I'm trying to think what your question is. Is your question, why is the antiderivative of this guy that guy?
Actually not. My question is why sine theta times tangent theta, which is original one, became secant theta tangent theta.
Not sure. Let me write that down. I think if I can write it down, it'll make more sense to me. So in question 21, if I pick it up correct, we have secant theta, tan theta, d theta with some numbers, and its antiderivative is secant theta. And the numbers in my example were these two. And so,
oh, Professor, I think I got it. I because
You-
that you write sin theta tangent theta, but it was actually secant theta tangent theta, right? It made sense.
Okay, it makes sense.
Yeah.
That's all that matters.
Yeah, thank you so much.
You are welcome. Any other questions? Okay, we'll keep going. Here's a version of 25. You will be doing antiderivatives for a long time, not just after this class, but into Calc 3, into Calc 4, and Diff 1 and Diff 2. You're going to do you're going to do integrals. So, and this is the beginning. So we're just kind of getting up to speed. But you know, the more practice, the faster this will get. What's the antiderivative of 9 of this fraction?
Would that be 9 inverse tangent?
And thank you for using inverse tangent. Yeah, evaluated at 1 over root 3. So if I called this step the calculus part, we're kind of finished. Is it the rest of what's going to harm? I'm basically just trying to find out what the value of this expression is at 2 places. And so what we're going to be dealing with is really math 142 stuff, right? The value, the exact value, if it's possible, of trig functions. So it's going to be 9 inverse tan of root 3, take away 9 inverse tan of 1 over root 3. And you might just say to yourself, that looks good to me. I'm happy, but I'm not. We could do better than that. So now we have to figure out what the exact value of these 2 guys are. Now, let me show you what you might do and show you why there's a problem with that. You might go into your calculator, probably put it in degrees because they're easier to see. And you might just say inverse tan of square root of 3. And the answer comes back as 60 degrees. And then you might do inverse tan of 1 divided by the square root of 3. And you get the answer 30 degrees. So that there is what angle has the tan of root 3, and that's 60 degrees. And this one is what angle has the tan of 1 over root 3, and the answer is 30 degrees. And don't write this down because it's going to be wrong. Oh, 9 times 60 degrees, take away 9 times 30 degrees. I guess I won't use the degrees anymore. And you come up with some really extreme big number. What's wrong with that?
It's not in radians.
Correct. Now, if you want to do that, won't you turn this into pi upon 3, because that's what 60 degrees is. And won't you turn this guy into pi upon 6, and that's what this guy is. And then this guy becomes 3 pi, and this guy here becomes 3 over 2 pi, and they together eventually get you 3 upon 2 pi. Now, is that not a much prettier answer than leaving it in this ugly form up here? So if you make your calculator in degrees so that you can get inverse sine of 1 over root 2, you know, any of those weird fractions or whatever you're looking at, please remember that the answers in calculus are pretty much universally radians. So make sure that anything that you deal with is in radians. Are we good? Thumbs up. Let's go. Next one. I'll pick my own. How about the integral from 0 to 2 of 4 to the power of t dt. Now, that guy there is this one. So its antiderivative is 4 to the power of t divided by the natural log of 4. And then you evaluate it at t equals 0 and at t equals 2. And you plug in 2, you get 4 squared over the natural log of 4. Take away 4 to the 0 over the natural log of 4. And that's 16 over log 4. Take away 1 over log 4. And that is 15 over log 4. Do you think that's as good as that's going to get? The fraction 15 over log 4, do you think that is it? Well, here's the nice answer, yes, that's it. There isn't anything you can do to log 4. On the other hand, if you got a question that looked like that, wouldn't you change it by rationalizing the denominator? God forbid you ever get a question that looks like this, but if you got a question that looked like that, wouldn't you make it look pretty? Because fractions shouldn't have fractions. And if you're wondering how do you fix this one, you multiply top and bottom by a special version of 1. And that's what it looks like. It's actually quite nice. So always have in the back of your mind, right at the end, am I finished? Can I make it look prettier? If you can't, you're finished. But if you can, yeah, make it look pretty. Still points. Okay. Question 28 has the function the square root of x, and it's got y equals 0 and x equals 9. And we're being asked to sketch this region. And it says a graphing calculator is recommended. I don't know if it is. Sketch this region. So we're just going to draw. What does that look like? And the reason why I don't think I need a graphing calculator is that I think everybody here knows that I'm not being perfect. Would you agree that's what square root of x looks like? I'm not being detailed. Now, x equals 9. Wouldn't that be this vertical line here? What is the line y equals 0? What does it look like?
Would it be the origin?
Well, the origin is a point. So what do you mean? The origin is just that corner. I think you're in the right track. If you just take it a little bit further, you'll be there.
Oh, I was
The
thinking like
x-axis.
if y equals 0, then x would have to equal 0 as well.
Ah, but if you're thinking in this curve, yes. But on its own, with no other information, what does y equals 0 typically give you?
It gets you on the x-axis, I guess.
That's it, yes. So there is the third one. I guess I'll have to put it in as red because you can't see it now, right? Now you put those three together. Isn't that description this guy? So when they ask you to sketch this region, they're basically wanting you to draw that picture. And then what you will see, but I'm not going to zoom to it because it takes too long, is you'll see 4 pictures, but one of them looks like that. And that's the one you pick. Now, I don't think it asks in a part B, but it does. So there's a part B that says, what is the area of that? Well, isn't the area of that simply just the integral from 0 to 9 of the square root of x dx? Agreed? Now, Square of x would probably benefit by being called x to the half. And then I'm going to do my dot, 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 dot. And you get the answer and you write it down. How about this one? This is 29. We have y equals x cubed, y equals 0, and x equals 2. Now you put that package together. Again, I don't think I really need a calculator to do that. Would you agree that y equals x cubed looks a bit like that? I mean, if you want to do the other side, it goes over there, right? Y equals 0 is the x-axis, and x equals 2 would be about here. So that's the region that you're going to be asked to sketch. You pick a picture from a choice of 4, and then to find that area, it's the integral from 0 to 2 of x cubed. And I'll just do a little dot, dot, dot on that, because that's pretty easy to finish. I'll put that there. I think we're almost done. Perfect timing. Here is this guy and this guy. Now, if you want to sketch him, I guess you might want to put that one in a calculator, it's up to you. But the way my brain works is, would you agree? It's a pretty primitive version of it, but would you agree that's what y9 minus x squared looks like? See the little cave shape? The y equals 0 is this fella. So there's your region. And then if you want to do the integral, now I know why they picked this one. If I want to find the area of this shape, don't I need to know what x that point is and what x value that point is? Don't I need to know those numbers? Would you agree they're pretty easy? You should be able to do it in your head. What would these two numbers be?
3 and -3.
Correct. For somebody who's not quite sure what the heck's going on, could you explain what you did to find those? Or how you knew it was 3 and -3, which it is?
Those are where y is equal to 0.
Right, you found the x-intercepts, right, when y is equal to 0. So if you plug 0 here and solve, you get it. Would you agree that guy there is a dot, dot, dot question? Can't you just do the power rule and plug in numbers and get 42, whatever the answer is? So far, so good? Right, I'm going to ask you to do, we're going to have a little look at some other questions in a moment, but for that, when you do high today, and if you've already done high, you're going to do it again. I'm spending far too much time getting registration done, right, when I check your things. And one of my problems is that I don't get your name the right way round. I get it like John Smith, right? But that's very hard to put in alphabetical order because then I have to go and find out which John and are you here. So what I'd like you to do, and I'll try it out, and if it doesn't work, then we won't do it. But instead of saying hi, will you say your name backwards? So type in, if your name's John Smith, will you type in Smith John? Because what I can do is then I can take the text file and I can put it in alphabetical order, and it'll be so much easier for me to do registration that way around. So instead of saying hi, will you say your name backwards, for want of a better way of saying it? Plus, it takes care of those people who are called Eric, because then if there's 2 Erics, I don't know which Eric is. And that makes my life a little bit harder as well when I have to do the registrar. So thank you for doing that. And while you're doing that, We'll get set up for. Get you set up for tomorrow. Okay, now tomorrow is going to be about two topics. It's going to be indefinite integrals and what's called the net change theorem. Sounds more important than it truly is. Right, indefinite integrals first. We already know what indefinite integrals are. It's these guys with the pluses. So they're not, it's not going to be anything new, right? You're just going to be asked to find, you know, pick some at random. You're going to be asked to find this guy. So it's going to be 4x good, 6x plus 3 dx. So the first half of chapter 5.4 is simply just going to be, you know, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, and remember to put a plus c. So in a lot of ways, aren't these questions much quicker because you don't have any number, you know, plugging in numbers and making it look pretty. Okay, now, indefinite integrals are also called general integrals. So just in case you see the term general integral, think of it as another name for an indefinite integral. And indefinite integrals are the ones that have plus c's at the end, right? What does a definite integral do then?
It would define what C would be.
Yeah, well, that's probably the way I phrased it. That's a definite integral. That's an indefinite integral. Do you see the difference? In a definite integral, you have numbers, right? You have limits of integration, 1 to 3. And when you do a definite integral, isn't the answer a number? I know it's not 42, but it's my favorite number, right? It's 42. And when it's an indefinite integral, isn't your answer a plus c? So although they're very similar, can you see that they finish at a different destination, right? So in these ones, you're going to finish with plus c's. Most of what we did today, didn't you finish with a number, you know, √2 or 42 or whatever it might be? Oh, cool. Yeah, we've got 3 minutes. Let's look at some weird ones while we're finishing. How about this fella? I like weird ones. I like puzzles. The 5th root of x plus 1 over the 5th root of x. So this integral is going to be the one with the plus c's when we're finished. Any ideas what the next line is going to look like? Because I can tell you right now, there's no way I'm going to be able to integrate those guys the way they're written. Agreed? So I got to figure another way to write them, and then I can find their antiderivatives I can integrate them. How would you write the 5th root of x?
1 over 5.
I'm not sure if I caught that right. Would you say it again?
X to the power of 1 over 5.
Correct. And what about 1 over the 5th root?
Negative power.
Are we all comfortable with that piece of algebra? Because if you don't understand that fractional powers can come out of radicals, and that 1 over fractional powers generate negative radical fractions, as they do here, then if you can't do that line, you're not going to get the question, right? So you need to get comfortable with that process. Now, the answer is going to be decidedly ugly. No, I'm not. It's ugly. Add 1 to the power. You get 6/5. Remember, we need top Ivy fractions. Divide by the new power. Well, dividing by 6/5 is the same thing as multiplying by 5/6. Are we all happy about all those ugly fractions and why we got them? Right, this one's even weirder. If you add 1 to that guy, he now becomes positive 4/5. And then if you divide by 4/5, it's the same as multiplying by 5/4. And you've got that guy. Are we finished, or is there some style points we should be doing here?
Do we have to put them back in the form we got them in?
Yep. So anybody want to have a shot at what 6/5 looks like when it looks more like these guys?
Square root of x to the 6th.
Well, I'll put the symbol down, but it's the 5th root because of that. And this one,
The 5th root of x to the 4.
plus C, and we call it good. I was going to do the next